Hey physicists, want to look at accelerated motion in a few more sophisticated ways here. If we're traveling at a constant velocity, we have our regular equation that the displacement, or the distance that we travel, is our velocity times our time. And in this case, where distance is measured in meter, velocity in meters per second, in time in seconds. We can graph that and also get kind of an appreciation for the units as well. So on my horizontal axis, I have time in seconds, and then on my vertical axis, velocity in meters per second. So if I'm at constant velocity, you can see I end up traveling at that rate. Let's say I travel for that period of time. Okay. I take velocity times time to get my distance. Well, I could also take a look at, this is a rectangle as well. I took up my velocity times time, and that actually ends up being the area of this as well. And let's notice that if I have, for a rectangle, the area of the rectangle is the base times the height. Let's put some units in there. We'll assume that, maybe we're traveling at 5 meters per second for 10 seconds. We'll put it into this formula as well. So I can see if I am at 5 meters per second for 10 seconds, putting in the format here, 10 seconds being the base, 5 meters per second being the height. I've gone 50 meters. Guess what? The area of that is, I can take my seconds, cancel them. I have 50 meters. Hey, let's take a look at if our velocity is not constant. In that case, our displacement is going to be our average velocity times our time. Perhaps our velocity is speeding up or slowing down. Let's see if we have a way of describing that velocity. And if we are under uniform acceleration, that velocity is equal to our acceleration times time. And I just want to cover the units we have here. Velocity, again, in meters per second, our acceleration in meters per second squared, or meters per second to feel more comfortable with that, and time in seconds. Now, if I am changing uniformly, then I know my average is really just equal to my beginning value. I'm going to call that velocity 1, and my final value divided by 2. So I've created this graph over here, and uniformly changing motion would just be our velocity versus time changing at some constant rate. Again, we can see the slope of that. Slope is going to be in meters per second, or meters per second squared, which is our acceleration. For this, I'm going to assume that I'm going to start at rest at 0 meters per second, and my final velocity then, velocity 2, is going to be equal to my acceleration times my time. Let's go ahead and do some substitution. So our average velocity is going to be equal to velocity 1 plus velocity 2 over 2, our average. Velocity 1 we know is 0. Velocity 2 from this equation I can see is acceleration times time. A times t, again we'll divide by 2. I'm going to substitute this value here back into my original equation, so I see that my distance is equal to acceleration times time over 2. I've dropped the 0 at the beginning, times time. I'm going to rewrite this just a bit. It'll make it look kind of interesting here. I'll write it as 1/2 times a times t times t. Remember that a, acceleration, is the slope of our velocity versus time line over here. Hey, let's go back and see if we can apply this idea about area over here as well. Up here we said that the area created by the rectangle of velocity versus time represented the distance that something traveled. Let's see over here what ends up happening. Let's take a look at the area here. Okay. And the area of a triangle, A, is equal to 1/2 base times height. Our units certainly work out. We have velocity in meters per second, time in seconds. So we know the area of this will be in the units of meters. Let's see if we can come up with a value. So 1/2, our base is time, and the height of this, that point right there, is going to be the slope of our line times the x value, which in this case is t. So that's equal to a t. Look at that. End up looking the same, equals to 1/2 a t squared, let's go ahead and simplify this, is equal to 1 half a t squared. So I've given a value here of acceleration is 4 meters per second squared, time for 5 seconds. Let's see if we can figure out our distance. Notice we don't have a velocity in here, so this is becoming a powerful equation for us. Our distance is equal to 1 half our acceleration, 4 meters per second squared, our time, 5 seconds squared. So I get, let's see, 1 half 4 meters per second squared times 25 seconds squared. I get a value of 50 meters. That's my seconds squared. Cancel each case here. Let's also take a look at what this type of equation is. This looks like that's right, a parabola. Okay, so if I was going to plot distance versus time, I'll do that here, or my position versus time, I would notice that the shape of this will end up being a parabola, and the value, at least at 4 seconds for this one, is going to be 50 meters. I'm going to get something that looks like where, in this case, this is out at 4 seconds. This happens to be 50 meters just for this particular case. Yeah, what you're starting to see some of the beginnings of calculus and how Newton looked at this, but actually the value of this function right here at 4 seconds, given this equation at 4 meters per second, happens to be the area under the curve. We'll use that term a lot in calculus, or the area bounded by this triangle in our velocity versus time graph. Hey, you might be saying, hey, I'm not always starting off at a velocity of 0. How else can I arrange this? Really, the equation becomes pretty simple, and we'll show you just graphically in a moment how that works out. So we end up just really having our distance is 1 half a t squared. We know that's the value for starting at 0 velocity. Plus, if we do have an initial velocity, I'm going to call it v1, just to be consistent with the book. Oops, sorry about that. v1 times t. Let's take a look at what that would look like on a velocity versus time graph. I'm going to assume that acceleration is positive here. Let's say we're starting at some value, velocity 1. And really, let's see, and this slope again is a. Let's take a look at the area here. I can divide this up into 2 sections here. So I'll go with my triangle up top, and I know the area there is described by this part of the equation, and then the lower portion just really is a rectangle, and you'll see that our velocity 1 times time looks very much like our equation, very up at the top here. Let's go back on down. And so base times height here is described by that part of the equation. So this equation can be used to describe the position or displacement of an object if we only have the acceleration, the amount of time, and perhaps an initial velocity. We don't need a final velocity to figure out how far our object has moved. What's also nice about this is that when we put in do the math, if we have negative values for velocity or acceleration, they'll end up coming out in the wash as well, and show that we'll have either a positive or negative displacement. We can go through one more step that's going to be pretty math intensive on this one. So we have, in addition to this relationship, we've just developed that distance is equal to 1 half times the acceleration times time squared plus our velocity or initial velocity times time. We also know that our velocity is equal to acceleration times time. If I have some type of an initial velocity here, I might call my velocity 2 is equal to my acceleration times time plus my velocity 1. You'll notice that both these equations have time involved, and sometimes I don't have the ability to determine what the time involved is. So I'm going to see if I can create a relationship that gets rid of time. So I'm going to rearrange this equation to isolate time. So I can say time is equal to velocity 2 minus velocity 1 over acceleration. Let's see if I can take this time and put it into this first equation and get rid of time and put everything in terms of v2, v1, and our acceleration. So my displacement is equal to 1/2 times acceleration times time, which I now know is v2 minus v1 over a squared plus v1 times v2 minus v1 over a. Whoops, notice my squared here. I forgot that the first time. Okay, I'm going to kind of change this around or just start simplifying equations. So I'm going to have v2 minus v1 squared, have my a out here over a squared plus v1 times v2 minus v1 also over a. I have an a squared term on the bottom here and a on the top here. I'll cancel those. So you notice both these terms are now over a. I have this funny 1/2 in front over here. So I'm going to multiply each side by 2a to kind of clear out the denominator. So here I go with the 2a. Okay, so I'll be able to cancel out a. I'll have a 2 in front here, this 2. Okay, so I get around to 2a d is equal to v1 minus v2, that value squared, plus 2v1 times v2 minus v1. Let's multiply all that out. We got our binomial here, so I'll have v2 squared minus 2v2 v1 plus v1 squared. That takes care of that term. Next one, we'll multiply all the way through. 2v1 v2 minus 2v1 squared. Let's go and see if we can cancel some of this stuff out. Okay, if I combine, I can see my minus 2v2 v1 cancels with my 2v1 v2, or it doesn't matter there, so goodbye there. I've got a v1 squared here. I have minus 2v1 squared over here, so let's go ahead and get rid of one of those and that. So I'm left over with 2ad is equal to v2 squared minus v1 squared. And the most common way you see this presented in physics, we'll do a little rearrangement. 2v2 squared is equal to v1 squared plus 2ad. Do the units work out? Let's check out whether they do or not. So let's take a look. On the left side, we have velocity squared, so we would have meters per second squared. That's going to be equal to a meter squared per second squared. Okay, how about on the right side? Well, one thing we know that velocity squared, yep, we're going to have meters squared per second squared there, so that checks out. And our last one, 2 times acceleration times our distance. So if we have 2, that's just a scalar. Acceleration is in meters per second squared, and our distance is in meters. Yep, units, that's going to work out fine. That's meters squared per second squared. So we have here are the big 3 equations of motion. Here they are. That velocity 2 is equal to our velocity 1 plus acceleration times time. Notice in this, there's no distance. Distance is equal to 1/2 at squared plus our initial velocity, velocity 1 plus time. Notice that there's no v2 in that. That's going to be helpful because if we have to solve a problem, we don't have that information. We don't need the information. This last one, velocity 2 squared is equal to our initial velocity, velocity 1 squared plus 2 times acceleration times time. Acceleration times distance, and there's no t. And sometimes the fourth equation here, the one for constant velocity motion. That distance is equal to average velocity times time.